I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will see the topic on plane waves in free space. This is for the course Electromagnetic Fields and Waves. So now the plane wave is an electromagnetic wave where its amplitude is constant over any plane perpendicular to the direction of propagation. In other words, we can say the wavefronts are infinite parallel planes. This means that at any given time the value of the wave is same on any point within a given plane. So this is about the plane waves, and now we are discussing the nature of plane waves. The plane waves are always transverse in nature because the electric field E and the magnetic field H are always at right angles to each other, that is perpendicular to each other, to the direction of wave propagation. So for example, if we consider the wave is propagating in z direction, its electric field will be in x direction and its magnetic field will be in y direction. So both the electric and magnetic fields are perpendicular to the direction of wave propagation, and the direction in which the wave moves is called the direction of propagation, and the wave maintains same amplitude and direction across any plane perpendicular to its motion. So, and now the free space conditions. So free space means a perfect vacuum, no obstacles, no charges and no currents. So now, if we consider the nature of electromagnetic wave in free space, it has no resistance, no attenuation, and travel at the speed of light. And this is the ideal environment to study the nature of electromagnetic waves, that is plane waves. And in free space, we are going to see some of the conditions. One is the permittivity of the medium. Permittivity is nothing but how the field is accepting to reacting to the electric field, that is epsilon is equal to epsilon naught, and the permeability mu is equal to mu naught, rho value is equal to 0, and the current density is equal to 0, because this is J is conduction current density. We know that free space is a perfect dielectric, so its conductivity value is 0. So these are a very important free space conditions. Okay. Next, we move on to the very important expressions which are very provided a base to the existence of electromagnetic waves, which are called as Maxwell's waves. And now the Maxwell's waves in free space we are going to see. There are four Maxwell's equations are available, and in that two are electric fields and two for magnetic fields, and two equations are curl equations, two equations are dot, that is divergence equations. So first we see the equation del dot E is equal to 0. This means that there is no electric monopoles. And the second Maxwell's equations for the free space, no magnetic monopoles, that is del dot B is equal to 0. Third equation is del cross E is equal to minus dou B by dou T. This Maxwell's equation is derived from Faraday's law. And the last equation, the magnetic curl equation, del cross H is equal to dou D by dou T. So this is the Ampere's law without current. So these four Maxwell's equations in free space are considered to be the absence of charges and the currents. Now, propagation characteristics and wave equation of uniform plane waves. So we know that plane waves travel in straight line with constant speed in free space. The energy carried by the wave moves forward continuously without loss, and the wave does not spread out like circular or spherical waves. And the wave equations, which are also called as Helmholtz wave equations, very popular. One is for in terms of electric field, and another one is in terms of magnetic field. So the electric field wave equation del squared E is equal to mu naught epsilon naught dou squared E by dot T square. And the magnetic field wave equations, the analogous equation del square H is equal to mu naught epsilon naught dou square H by dou T square. So these two equations are called as wave equations for free space. And now the plane waves electric and magnetic fields. So in the diagram, the electric and magnetic fields are perpendicular to each other. So this we have observed from the nature of plane waves. And also they oscillate when they move forwards, but they are always perpendicular to each other. And their strength and direction are uniform across any plane of the wave. And now the importance of free space and its applications. So the uniform plane wave or electromagnetic plane wave concept is used in antenna design and analysis. So in the antenna design and analysis, we need to observe how the wave is propagating through antenna or how the wave is receiving from the antenna. So in order to see the analysis, the plane wave concept is very important, and they are also very much useful in wireless and satellite communication. And plane wave concepts are very important for radar systems and the transmission lines like optical fibers and also the laser systems. And these plane waves concepts are very helpful in understanding how a signals travels through air or vacuum. And a uniform plane wave is an idealized case. It can adequately model many practical situations in wireless communications, radars, etc. For example, fields impinging on antennas that are far away from transmitting antennas are practically uniform plane waves. Now, the assessment questions. The properties of uniform plane wave we have seen from the nature. Electromagnetic characteristics we have observed, and the importance of uniform plane waves we have seen from the applications. So these are about uniform plane waves, and they are their properties in free space. Thank you.